Beautiful. Right.
Factor of safety. It is defined in general as the ratio of maximum stress to the working stress. So materials will have some failure value. So if they are stressed up to the failure value, then immediately the member will get failed. In order to use the member made of certain material repeatedly over a period of time, we should not stress it up to the failure value of stress. So the operating stress or working stress is obtained by dividing the maximum stress with a number. That number is called factor of safety. This factor of safety will depend upon certain things. Those things are especially if a member fails, what would be the outcome? The outcome may be measured in terms of catastrophe, that is, effect to the human life or effect to the machinery or the production itself. If it results in very heavy casualty or uh, very heavy losses, then definitely we are going to use greater number of factor of safety. That means there will be a wide gap between the maximum stress or failure value of stress to the working or design stress. If the failure of the member doesn't affect many things, then you can go with a smaller value of factor of safety, maybe 1.25 or 1.5, like that. If it is very very important, then we need to go for a factor of safety of the order of 5, maybe 8 or 9 or even 10. In the ductile materials like mild steel, etc., the failure value of stress should be taken as the yield point stress, whereas in the brittle material like cast iron, we will take the ultimate stress. Principal stresses and planes. When the member is subjected to uh, more than one axial directional stresses along with the shear or without shear, the failure value of stress will not be any one of these stresses, and it would be much higher than the applied value of stresses. So that value is calculated by the principal planes and principal stresses. The principal plane is the plane uh, on which there is no shear stress acting, and principal stress is the normal stress acting on the principal plane. Here you can see a member subjected to biaxial state of stresses sigma 1 and sigma 2, and on which we have taken an inclined plane at theta degrees with the vertical. The normal and tangential stresses on this plane can be calculated, and when this angle theta becomes some value where the shear stress on this plane equals to 0, then this inclined plane will become the principal plane, and the normal stress on that principal plane is known as principal stress. There are two principal planes. Uh, each of them are right angles to other, and on one principal plane, the maximum value of normal stress acting, that is known as maximum or major principal stress. The other one is the minor principal stress. And we also have uh, maximum value of shear stress and the minimum value of shear stress. Uh, those can be calculated by the formulas here. The principal stress is sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta and tau sin 2 theta, and maximum value of shear stress is sigma 1 minus sigma 2 by 2 sin 2 theta minus tau cos 2 theta. And then we move on to the theories of elastic failure. There are a number of machine components which are subjected to several types of loads simultaneously and induces combined stresses. If we take the example of a power screw, it is subjected to torsional moment as well as axial force. An overhang crank is subjected to both bending as well as the torsional moment. Likewise, certain machine elements are subjected to a complex state of stresses. The failures of these machine components can be broadly classified into elastic as well as the fracture. Elastic failure results in excessive elastic deformation, while yielding results in plastic deformation. Fracture is the result of breakage or the separation of the component into two or more pieces. The theory of failure applicable to the elastic failure of the machine parts. The mechanical properties are obtained in the simple tension test. However, it's not possible to conduct a different tests for different possible combinations of the loads. Uh, and obtain the mechanical properties. The theories of elastic failure provides a relationship between the strength of a machine component subjected to complex state of stress with the mechanical properties obtained in the tension test. There are total five theories of elastic failure, and they are maximum principal stress theory, also known as Rankin's theory, and maximum shear stress theory. It is also known as Coulomb Guest-Trescas theory, distortion energy theory, and maximum strain energy theory, and maximum total strain energy or distortion energy theory. Out of these five, maximum principal stress theory, maximum shear stress theory, and distortion theory are most widely used. Let us discuss on these three theories of elastic failures. The first one is maximum principal stress theory. According to this theory, the failure or yielding occurs at a point in a member when maximum principal or normal stress in a biaxial state of system reaches the limiting strength of the material, that is either the yield strength or ultimate strength in a simple tension test. So the maximum principal stress is obtained by dividing the yield point stress with factor of safety for the ductile material, whereas ultimate stress by factor of safety for the brittle material. Next, the maximum shear stress theory. According to this theory, the failure of the member occurs when the maximum shear stress in a biaxial system, biaxial state of stress system, the value of shear stress in the yield in a simple tension test. That means the maximum shear stress that is obtained from a member which is subjected to biaxial state of stress, when that equals to the shear stress at yield point in a simple tension test. In other words, we write the tau max is equal to tau yield point stress by factor of safety. Since the shear stress at yield point in the simple tension test is equal to half of the yield stress in tension, now we can rewrite this as tau yield point stress is as sigma yt by 2. That is, the yield point stress is half of the, uh, rather twice of the yield point shear, or in other words, the yield point shear is half of the uh, yield point tension or normal stress. So this theory, maximum shear stress theory, is suitable for designing the ductile materials. And third theory is von Mises theory or distortion energy theory. According to this theory, the failure or yielding occurs at a point in a member when distortion strain energy, also known as shear strain energy per unit volume in a biaxial stress system, reaches the limiting distortion energy per unit volume as determined from a simple tension test. Sigma T1 whole square plus sigma T2 whole square minus 2 sigma 1 and sigma 2 is sigma yield point by factor of safety whole square, where sigma T1 and sigma T2 are the maximum principal stress and the minimum principal stress in the Bagdell stress system, and sigma yt is the yield stress obtained from the simple tension test, and factor of safety is FOS or FS. This theory is also suitable for the designing of the ductile materials. Here we can see some examples. So let us look at the example 1. The load on a bolt consists of an axial pull of 10 kilonewton together with a transverse shear force of 5 kilonewton. So here a bolt consists of an axial pull 10 kilonewton and there is a transverse shear force of 5 kilonewton. It is subjected to both kinds. One is the tension and another one is the uh, shear force. We need to determine the diameter of the bolt according to all the theories. I'll take the permissible tensile stress 100 MPa and Poisson's ratio 0.3. So you know that the axial tensile stress is the load applied by the cross sectional area. What is the load applied here? It is subjected to a pull of 10 kilonewton. So 10 upon the cross sectional area, that is pi by 4 d square, where d is the value to be found out, and then the transverse shear, that is the transverse force upon the same cross sectional area. So here the member is subjected to 5 kilonewton. So 5 kilonewton upon the area of the member. Now, according to maximum principal stress theory, the major principal stress or the maximum principal stress is equal to the failure value of the member with the given factor of safety. Now, in this case, there is no factor of safety given. Now, we directly take the major principal stress equal to the failure value of the member. Here, the failure value of the member is given as the permissible tensile stress. That means the factor of safety is included, and hence we take straight away the fact failure value by factor of safety as the permissible or working or design stress, that is equal to the value of major principal stress. So here there are two types of stresses induced in the member. One is the normal and another one is the shear. So sigma 1 by 2 plus uh, half of square root, within the square root we have sigma 1 square plus 4 tau square. So sigma 1 is the normal stress and tau is the shear stress. By substituting these values, we got the diameter as 12.4 mm. This is by maximum principal stress theory. Let us look at the second one, maximum shear stress theory. So tau max is equal to half of square root of sigma 1 minus sigma 2 whole square plus 4 tau square. Let us substitute the sigma 2 as 0 and sigma 1 is the calculated normal stress and tau as 6.35 by d square. And we got uh, tau max should be taken as half of the sigma t1. So sigma t1 is given as 100, then tau max should be 50. So this maximum shear stress should be equated to this 50, and the value of the diameter can be found out, and it is 13.42. So according to maximum shear stress theory, the diameter is found out as 13.42. And third one is distortion energy or von Mises theory. So according to von Mises theory, so it is sigma t1 whole square plus sigma t2 whole square minus 2 sigma T1 into sigma T2 is equal to the failure value of stress divided by the factor of safety at elastic limit whole square. So here in this case, the working stress is given, so that is failure value upon the factor of safety. So that is given as 100. So 100 square is equal to sigma T1 and sigma T2. There is no sigma. So from this value obtained is also 13.4. So here uh, sigma T1 and sigma T2 are the maximum and minimum principal stresses, or these are also known as the major principal stress and minor principal stress. Sigma T1 is the major principal stress and sigma T2 is the minor principal stress. So you can find out the minor principal stress as sigma 1 by 2 minus half square root of sigma 1 square plus 4 tau square. So this is obtained as minus 2635 by d square, whereas the major principal stress is uh, that is 15365 by d square. So these two are substituted here and they are equated to 100 square, and with this we got a value of diameter 13.4. So from the maximum principal stress theory we got 12.4, from maximum shear stress theory we got 13.42, and from the distortion energy we got 13.4. These are the three different values we got But when we consider the member as the ductile material, the values are coming closer to each other. Similarly, we can take one more example. Here, a cylindrical shaft made of steel of yield strength 700 MPa is subjected to static loads consisting of bending moment 10 kilonewton and a torsional moment 30 kilonewton meter. Determine the diameter of the shaft using two different theories of failures. Assuming factor of safety 2, take E 210 GPa and Poisson's ratio 0.25. So here the member is subjected to both bending as well as torsional moment. So bending stress found out from the bending moment upon the section modulus, and then the torsional moment is obtained by T is equal to pi by 16 d cube into tau, and from that you can write the torsional shear stress is 16 T by pi d cube. So in both these, you have the unknown value, the diameter d. When we substitute these two, there is only one stress, that is single directional normal stress, that is sigma 1, and there is a shear. So again, the principal stress expression will be condensed to sigma 1 by 2 plus half into square root of sigma 1 square plus 4 tau square. So after substituting these normal and shear stresses, we got the diameter of the member as 97.2. So what we have done here, the according to maximum shear stress theory, this is sigma T1 minus sigma T2 by 2. That is, sigma T1 is the major principal stress and sigma T2 is the minor principal stress. So here we take plus symbol between these two, we will get the major principal stress, and the minus symbol we got the minimum principal stress, or it is also known as minor principal stress. And the first one is 211.9 into 10 power 6 by d cube, and second one is minus 110 into 10 to the power of 6 by d cube. So by substituting these two, we got the diameter as 97.2. Tomax is the allowable shear stress. We got the uh, 700 MPa is the yield strength. So divided by 2 will give us the yield strength in shear, and we also got the factor of safety as 2. So that is 700 by 2 350, 350 by 2 is 175. 175 is the allowable shear stress, and that is equated to this 161 into 10 power 6 by d cube. From this we got diameter as 97.2. According to the maximum principal stress theory, we are equating the major principal stress to the allowable uh, normal stress. So yield point stress upon factor of safety, that is 350. So 350 is equated to 211.9 into 10 power 6 by d cube, and we got d as 84.59. So from the maximum shear stress theory we got 97.2, whereas from maximum principal stress is 94.59. So these are the two theories of elastic failures. One is suitable for the brittle material, and another is suitable for the ductile material. So likewise, we can take many examples. Here we can take one more example. You can see here a structural member uh, having one end fixed, the other end is free. Close to the other end, here is a pulley, and a wire rope is attached uh, at the fixed end, and it is passing over the pulley, and it is holding a weight of 5 kilonewton, and its cross section is rectangular, w width and depth d, and up to the center of the pulley the distance is 1500 from the fixed end, and there is another 500 beyond the center of the pulley in the horizontal as well as in the vertical direction as shown in the figure. So this will result in uh, how many things? One is the bending. So bending moment is the 5 because we don't have the diameter of the pulley, so therefore it is 1500 into 5 kilonewton, and then this 5 kilonewton, when it is shifted to the center, this will be 5 downwards along with 5 into the radius.